Okay, hi guys. So in this lecture, we'll be talking about the intensity of light. Okay, so let's get started. So intensity of light is simply defined as the number of incident photons per unit area per unit time. Okay, so just remember this: number of incident photons per unit area per unit time. So intensity is number of h nu over a into time. So this is the number of photons incident per unit area per unit time. Number of incident photons, this is unit area, this is unit time. Okay, so you can say that at constant frequency, intensity is directly proportional to the number of photons. Okay, next we have that let's draw a graph of photocurrent with frequency of the incident photons. Okay, so when till this point, when nu is less than nu naught, there will be no photocurrent. Then photocurrent would gradually increase to a point where you can have distinction between I1 and I2. You can say that where I2 is greater than I1, so more the intensity of light, more ejection of photo electrons from the metal surface will take place. Okay, and more would be the photocurrent. Okay, so you can just write this like that: as the intensity of light increases, the number of photons incident on the cathode electroplate increases, and hence number of electrons or photoelectrons also increases, resulting into more photocurrent. Okay, so kinetic energy of photoelectrons is independent to intensity of light. Okay, and why we are saying that kinetic energy of photoelectrons is independent of intensity of light, because the intensity of photoelectron, or the rather intensity of the photons, is will actually increase the number of electrons which are getting ejected from the metal plate or the cathode plate. It will not have any impact on the velocity of the photoelectrons that have been ejected. It has to do something with the number of photoelectrons which are getting ejected from the metal surface, not with the velocity of the photoelectrons which are getting ejected. Hence kinetic energy is actually independent of the intensity of light, and rather we should say that photoelectrons ejected will increase with the increase of intensity of light or photons. Okay, when nu is greater than nu naught. Okay, so let's now talk about stopping potential. So stopping potential is EV naught. Okay, so we can say that stopping potential is equals to EV naught and EV naught should be equal to kinetic energy max of the photoelectrons should be equal to half mv square. Okay, so I hope you know the form that power equals to energy per unit time, or and energy equals to V voltage into current into time. So power would be equals to, or rather you can derive the value of power from here. Okay, so power would be equal to Vi. Okay, so this was just a simple thing which I, or a rather a side note which I wanted to make. So let's get back to the original context of stopping potential. So therefore EV naught is equals to, what is kinetic energy? Kinetic energy is nothing but h nu minus h nu naught. Okay, so from here we can calculate the stopping potential as h nu upon E minus h nu naught upon E. Okay, so stopping potential can be defined as the minimum potential which is required to stop photocurrent at, and the corresponding energy is called stopping energy. Okay, so this stopping potential must be applied, which should be equal to the kinetic energy. Okay, so we know that from the left hand side photoelectrons were getting ejected from the cathode rays and coming to the positive charge plate. So this is the stopping potential which must be required here to stop the coming up of these electrons. Okay, so the energy of, or the rather kinetic energy which of the electrons which are getting ejected from the cathode is this. So this is the energy which must be applied from the stopping potential or from the external potential. So external potential would be, this much energy must be required to stop the coming photoelectrons, or from the electrons to get ejected from the cathode plate. So we know that energy is equals to VIT, which we just discussed here. Okay, and we know that I equals to coulomb, or rather charge upon time. Okay, so IT can be replaced with charge, and charge of electron is E. Okay, so VE was the energy which must be applied, where V is the potential and E is the charge on electron. Hence we wrote EV naught. V naught we represent by stopping potential. So stopping potential energy would be EV naught. Okay, so EV naught must be equal to the kinetic energy of the photoelectrons which are getting ejected. So this much energy would be should be applied in reverse direction to stop the ejection of photoelectrons. Hence EV naught is the energy which is required. And how much is the kinetic energy? We discussed in the previous lecture that, or that kinetic energy would be energy of photons minus energy of, or rather threshold energy. So this would be the energy of electrons or photoelectrons. Hence stopping potential would be h nu by E minus h nu naught by E. So I hope the derivation is pretty much straightforward and clear to you. So minimum potential required to stop photocurrent is called stopping potential. Okay, and the corresponding energy is called stopping energy. Okay, so with this we come to an end of this lecture. In the next lecture we'll be continuing our discussion on stopping potential, and we'll be seeing some graphs as well. So till then, good luck and goodbye.